Alright, today we're going to fill in the rest of your notes. It should say 7D. If you haven't done so, please take out your notes so that we can fill those in. And what we're going to be talking about is we're going to be talking about different types of crystals / different types of solids. Okay, and that's ultimately what we're trying to think about. And hopefully there should be the yellow concept map that we drew the other day that has the inner particle forces up on the board. That summarizes intra versus intermolecular forces, and that's going to dictate what type of crystal that we have. And we're going to write down 6 things. 1, the type of crystal, what force it's holding it together, what the lattice structure is or the points on the lattice, whether or not it has a high or low boiling point, if it conducts electricity, and an example. Alright, so the first type of crystal we're going to talk about is going to be ionic. So you're going to want to fill this in, and also if you don't get all this jotted down, this will be on eChalk so that you can watch it again if you need to. Alright, the first type of crystal is ionic. So that's going to be a crystal where the particles are being held together by ionic bonds. Okay, so you're going to have cations and anions as your lattice structures. And then because ionic bonding is so strong, okay, because it's so strong and it was part of those inner particle forces, they're going to have very high melting points and very high boiling points. Okay, so it's going to take a lot of energy to break up that ionic bonding and get it where it needs to be. Now for conductivity, and this just means will it conduct electricity or not, these are good when they're dissolved in solution, but not so good when it's the crystals only. And sodium chloride or regular old table salt is our sample here. And plain old solid table salt is not a good conductor, but if you can dissolve it in water, then it's going to be a pretty good conductor. Okay, so that's going to be our first type of crystal. Alright, the second type of crystal that we're going to have is going to be what we refer to as covalent network. Now covalent network is kind of a special type of solid, but ultimately the nice part is that covalent network is held together by covalent bonding. Excuse me, and again, if you look at that inner particle force diagram, the 2 strongest forces that we listed were ionic bonding and covalent bonding. And you're going to have single atoms that are held together. Most commonly with covalent network, they usually are carbon atoms or silicon atoms, but they're going to be single atoms. And I'm going to draw some pictures of these when we go over the study guide that will hopefully make this easier to understand in terms of what's on the lattice point and what forces hold them together. Now because covalent bonding is also very strong like ionic bonding, they're going to also have very high melting points and high boiling points, meaning it takes a lot of energy to break up that covalent bonding and allow those things to separate. Typically, if we think about conductivity, covalent network are usually non or semiconductors, pretty poor conductors. And 2 of the most common examples that we have of these are diamond and quartz. And even if you don't know a ton about diamond, we know that they're very strong. It takes a lot of energy to break them apart. That's why they're used in drilling and dental implants and stuff like that. Okay, alright, so let's go ahead. I don't think this is going to stick, so I gotta erase that. So if we scroll down to the next one here, oops, helps if I go back to the mouse. If I scroll down to the next one, okay, the next one I'm going to have is metallic bonding. Okay, so these first 3 all go with our intramolecular forces, or particles that hold atoms together. Intra. Whoa, I'm going to run out of space. Okay, so metallic solids, which are just metals, things like gold, copper, nickel, aluminum, all those things we can think of, are held together by metallic bonding. And metal atoms are what are on the lattice points. And I'm going to draw a picture of what I mean by this lattice point here in a little bit, and hopefully that will make more sense. But the thing with metals is that typically they have very high melting points and very high boiling points, but they also vary greatly. You have things like mercury that's a liquid at room temperature, up to things like copper and iron that have very high melting points, so it just depends. And because the metallic bonding, you have the sea of electrons, okay, it means that just like we saw before, they have very high electric conductivity, and really any metal that we can think of, things like copper, aluminum, zinc, gold, really any of those common transition metals would fall into that category when they're all by themselves. Okay, so that's going to be our metallic bonding. All right, so now we're going to depart from the solids held together by intramolecular forces and not skip, but move on to the solids that are held together by intermolecular forces. All right, let's see if we can do this correctly. All right, the first one that we're going to have here, and we're just going to separate these into two groups. They're either going to be polar covalent molecular crystals, okay, and if we haven't had a chance to totally review polar versus nonpolar, oops, that's not what I want to do, polar versus nonpolar, we will the next time that I see you, but polar covalent molecular crystals are held together by one of two types of IMFs, either dipole-dipole interactions or hydrogen bonding. Okay, that's going to exist, and what's going to be on those lattice points are polar molecules, and again, I'll draw you a picture of this here in just a minute. In general, they usually have lower melting points and boiling points than our metallics, our covalent networks, and our ionics, but they are slightly the nonpolar that we're going to see in just a minute. They're usually non-conductors of electricity, and water is one of the best examples of these polar covalent molecular crystals, which is held together by hydrogen bonding. Okay, and again, if you need to rewatch this video, it will be in eChalk. Alright, so you've got polar covalent that are one type that are held together by IMFs, and then the other type, and our last type of solid, is going to be nonpolar covalent. Now it's going to come back to our sharing or positives and negative ends or not, just like we saw with Unit 6, and like I said, we'll do some more work on this and review it, so hopefully we can polish this up a little bit. Alright, so for our nonpolar covalent, they are also held together as IMFs, just like we had up here with polar. However, okay, the only thing is that instead of the dipole-dipole or the hydrogen bonding, they're the ones that are held together by London dispersion, which are the only IMFs present in nonpolar crystals or nonpolar molecules. So again, nonpolar is going to be what's at the lattice point for these. They typically have very low boiling points and very low melting points. These are things that are mostly found as gases at room temperature, things like methane, octane, you know, all of these things that have carbon dioxide, hydrogen gas, all of these are nonpolar molecules. They're also non-conductors, and like I said, you have methane over here, which is a gas that we're pretty familiar with. Another one also would be carbon dioxide is also an example of a nonpolar covalent molecular crystal. And I know, I got to mention this, I know that carbon dioxide and methane are gases at room temperature, but this would be if we could lower the temperature enough in order to get to a solid. When we talk about these different types of solids, that's when we can classify them and kind of categorize them that way. So that's where it comes from. Okay, let me just illustrate just a little bit this whole idea of lattice points. So if we just look at ionic versus, let's do polar covalent. Okay, if you look at, and I don't have my, I'm trying to type with my mouse pad here, so, or write with my mouse pad. Okay, so polar covalent, close enough. Okay, if you're talking about an ionic crystal, when I say what's on the lattice points are ions. So for example, if I have sodium chloride, my ions are what are on the lattice points. I like to think of them as Lincoln logs. So the little circles would be the ions. And if you think about the sticks that hold the Lincoln logs together, those are the forces that are holding those particles together. And for an ionic crystal, it's going to be an ionic bond. Okay, so the ionic bond is what is going to hold the sodium and the chloride together, and that's a pretty strong bond. That's why salt, plain old solid salt, melts at a fairly high temperature, because that force is really strong. Now if we come over to polar covalent, if we think about water, okay, this is what's going to be different. The points on the lattices, or on the edges of the cube, the Lincoln logs, however you want to think of it, are going to be water molecules. Okay, which is a polar molecule. And again, if we haven't differentiated those in class yet, we'll do that the next time that I see you. Okay, so you've got water molecules. And since it's an intermolecular force and it's polar, the force that we have to overcome or that's holding them together is hydrogen bonding. So, oops. Hydrogen bonding, which I don't like the term because it's not conducive with being straightforward, but that's just the way it is. So that's what I mean with what the points on the lattices and then what is actually holding them together. And we'll spend some time going over this in the future, but I hope that helps, and I'll get your questions answered next